work together here. Let's talk about some of the things that y'all have so far. Somebody just shout out some of the stuff that you've noticed. We'll go back to you first. Emily and Belle, so no shouting, please. What are some things that y'all have noticed, ladies? Emily, did I say Emily?
Yes.
Sorry, Miranda and Belle. My mouth is going faster than my mind here. Go ahead. What do you got, ladies?
Tension changes the speed the wave moves throughout the string.
Okay, let's check that. I've got high tension right here. I'm going to go low tension. Oh, you are correct. Tension changes the speed. Okay. And so lower tension, lower speed, higher tension. This kind of relates to something we talked about before spring break, that the speed of a wave depends on what? Does anybody remember? The speed of a depends on the medium, the properties of the medium. Okay? So I'll put on normal speed here. So it doesn't really matter how high the amplitude is, so high or low amplitude, you'll see those guys are both traveling at the same speed. The one that has a higher amplitude is not moving faster. They're both kind of going the same thing. Belle, did you have something you wanted to add on to that?
Me?
Yes, another thing that you all learned or noticed.
No damping causes.
Oh, I want Belle to answer this one.
Me?
Yeah, you.
Changing the damping changes the distance the wave moves throughout the string.
Okay. So damping. So right now it's going all the way through. If I put lots of damping, oh, it kind of died. Somebody else talking about damping. How would you describe it? They said it relates to the distance that the wave travels along the string. Anybody have something different?
What I put was because for mine, like I didn't really change the damping much, so it just looked like the waves were getting shorter. So I said that as dampening increases, the amplitude of the wave at the end is less than at the beginning.
Okay. So as you have more damping, then the wave diminishes. Okay. What might cause damping? Anybody have an idea?
Friction.
Yeah, friction. Yeah, it's just basically a way of talking about the friction. We could also, what about the properties of the rope here? What property of the rope might affect the damping?
Material?
Okay, the material. Maybe how heavy it is, right? If you look at this right now, that looks kind of like a very heavy chain, right?
Mm-hmm.
But if I put low damping, you know, that kind of looks like a
Won't the tension also affect
tension. Yeah. Well, I mean, tension is going to affect how far, you know, the speed at which it's going through. So right now, since I've got low tension, it's going pretty fast. But so that's what's going on. No damping. This is going to go on forever. There's no friction. So this is never going to stop. Okay. Ivan and James, what's something that y'all noticed?
The higher the frequency, the bigger the number of drops.
Okay. So it looks like you went to the oscillate. And maybe we could, alright, just kind of go, let's see. This is high tension. This one's good. Let's put damping. You said the higher the frequency, the higher the what?
The bigger the number of waves, so to speak.
Okay. So we kind of get an idea. I can see about higher frequency. Okay. And that is what we would expect. Higher frequency. We've got more waves going down here. Interesting. We also have, once it hits over here, they reflect back. And so there's more waves. Yeah, it's... Did anybody try doing this with no damping?
Yeah, I went all crazy, like...
What in the... Yeah, what's going on?
I hear its whole instructions going.
Or then it starts getting like bigger and then
to one
smaller
direction,
and
then it like collides and pushes it the other direction.
Okay, okay, so let's try no damping, high tension, oscillate. Okay.
What did you say that was
called? When it was like, yeah.
Like a standing wave. We kind of got lucky on our last one. Whoa! That's crazy. Are you talking about when it cancels it out completely?
No,
Or-
when it does like this end does what this end is doing with this end.
I think
it's
like
you're talking about a standing wave.
Yeah.
I think it's what you're talking about.
You
Because
said
the
when it
middle
cancels out
points don't
completely, that's
move.
the total something.
Total destructive
Destructive.
interference. Right there. It just canceled it out completely. Huh, okay, so we can, there's some interesting effects going on here. Let's see if we can go this. James, did you have something you wanted to add?
Not really, no, nothing that's different.
That's fine, okay. Okay. Alex, anything new?
And oscillate, whenever you put the amplitude set to 0, there's no waves.
Okay, when you put what down to 0?
Amplitude.
Amplitude, okay, yeah. So the amplitude, that's changing how high it's going, and so if we put amplitude down to 0, I mean, it's according to this, it's spinning, but we're not moving the piston up and down at all. Okay, so it's literally like we just we're doing the same thing as we've got it clamped over here and we've got it clamped over there, and so this is kind of cool. You can kind of see.
They're traveling through it.
Yeah, the wave is coming over here. It's hitting here. It's going back, and it's hitting that, and it's going back.
What if it was a loose end though?
Okay, well, I can make this a loose end, and so this is one of the things, although this is kind of hard to see what's going on. I think a pulse, let's look at this, we'll make a kind of a high amplitude, a little bit of lower width. So let's talk about a fixed end. This actually we're not going to talk about till later on in the chapter, but it's a perfect time for us to discuss it right now. I hope I hit record.
You did.
Okay, great. Thanks. So, talk to me about a fixed end when a wave. Now, this is a wave. You might be like, "That's not a wave. It's not sinusoidal." It's a wave. Okay, it's a wave pulse. All right, and we've added energy to this rope a few moments ago when I hit that button and it went up and down. But this is a wave and it's going along that rope. Talk to me about what happens when it hits a fixed end.
It inverse the amplitude.
Yeah.
Switches, flips, inverts. Yeah, that's all good ways of putting it. So you can see fixed end here, so it flips down negative. When it hits over there, flips up top, and negative of a negative is a positive. The enemy of my enemy is my friend, so to speak. But look at the loose end. So it comes up, pulls this up. Do you see the difference there? Yeah, it's kind of cool if you watch it in slow motion. It'll be kind of go here. So you're like, why does it? With the loose end, it stays at whatever it is. If it's positive and hits the loose end, then it comes back positive. Well, watch this. Remember, the thing that's causing the wave is the tension. This particle right here is being pulled up by this particle, which is being pulled up by this particle, which you guys say, and it's being pulled up. It's sort of going all the way down the line. So this guy here is about to be pulled up by that guy. Yep, he's starting to get pulled up. Now this one gets pulled up. Now this one gets pulled up. Now this one gets pulled up. And eventually they get pulled up. You say, well, why was this one pulled up? Well, because this one pulled him up. And why was this one pulled up? Well, because it was pulled up by here. Where's the beginning? Who started this train here? And the answer is me when I hit that button and it pulled up and then it pulled back down. And so it's like it's remembering that thing which happened. Okay? So as we inch it along, this guy now is going to pull up that ring. So see, he pulls up that ring. And then this bar here is going to be pulled down on that green ball. And this one's getting pulled down because he's getting pulled down, because this one's getting pulled down, because that one's getting pulled down. And so he's going to pull the ring back down. And that's going to pull this one down, which is going to pull this one down, which is going to pull this one down. So you kind of see So like it pulls it up, and then the ring just is up there, and then it drops. And the opposite happens down over here. And what happens if there's no end?
It just keeps going and going.
Wave bye-bye, and we're done. Okay, so so no reflection on that one. I like the fixed end here. Now, let's talk about something. I'm going to send a pulse through here. What I want us to talk about, what happens when one pulse hits another pulse. All right?
Big flip.
I don't know
If they're opposites, then they'll flip, but if they're the same, then they'll just kind of be big.
Okay. I'm going to make another one with, I guess maybe the same amplitude, but I'm going to make the width a little bit wider. Okay? I wish I could make a rectangle one, but I can't. So here we go. All right, eyes up here. You don't worry about the rest of your notes because you're going to do it right here. Oh, I hit it twice. Hold on a second. Now it's just looking crazy. All right, manual. Nope. Pulse. It's got high amplitude. We're gonna go like pretty high amplitude there. And no damping. High tension, sure. That should go along forever. Now I'm going to lower the amplitude about half. And I'm going to increase the pulse width. So that it's very clear that you can see I've got two waves going along there. Now what happens when they meet? What happens when two waves meet?
Could you put it in slow motion?
It's like when you.
Yeah.
It's like if you're adding them together, pretty much.
Yeah.
Yeah, it is. It's like,
So average of the two.
yeah, it's like, well, yeah, this one, if, we'll go super slow motion here. All right, so this one's coming along, the shark fin, and then over here we have like the dip. So, forces are about to meet. Right? So the shark fin is going to want to pull this guy up, and this one right here is going to want to pull it down. And so it basically pretty much stays in the same spot. You with me, James? Okay. Then the shark fin is going to want to pull this guy up a whole lot more, and this one's going to pull it down, but not so much. So what we should see is we should see this one go up a little bit more up than it does go down. You see what's going on? So it's not going as up as much as the one was previously when he was left all by himself, but as these two start to converge, what we'll see, like, wait a second, what's going on? Well, the dip is now halfway through here. Okay, you can imagine that the dip's here, and the shark fin is like this, but the shark fin is getting diminished because this the trough over here is pulling it down. So when they end up being completely overlapped, you end up something kind of like this. Can y'all see the shark fin?
Mm-hmm.
Not as high as it was, right? He's kind of lowered a little bit. And this this trough, you can see where it would be naturally, okay? And you can imagine where the shark fin would be naturally. But when these two waves collide, what happens is the string just says, oh, according to this guy, I should be going up by 5. According to this guy, I should be going down by 3. Okay, looks like I'm only going to go up +5, -3. Okay, I'm going to be at +2. And it just does that for every single point and particle along the wave. And then they pass through each other. And they just keep going. So that's one of the really interesting things about waves, is that if you have one wave going one way and the other wave going the other, they just pass through each other. Okay? Ivan, say hello.
Hello.
Hello, Ivan. I need you to talk. Say like a whole entire sentence, like, hello, my name is Ivan and I like math and science, something like that. And while he's talking, I'm going to be sending other waves going in that direction, and we'll see what happens to them. Ready?
Wait.
Good. Just say a sentence.
Pull up your English and start reading.
Keep going. Also, while he's talking, I'm going to continue to keep talking.
Okay, the
But,
process of locating
his name is Ivan, and he actually likes math and science. But one of the interesting things is their waves are both colliding, but they're passing through each other. Okay? And so that's what's going on right now. Thank you, Ivan. Good job.
What were you reading?
I wanted to find some. Yeah, what were you reading?
My notes.
Oh.
I was like, what?
So at some point between Ivan and myself, those sound waves were hitting, colliding, you know, kind of going crazy for a minute, but then they would pass through each other. And that's what we saw here. Now, did anybody see my special sort of, I want to restart. Okay, that's the right one. I want the restart, not the reset. Okay? So anybody see this? Okay.
How many waves do we see?
Oh, well, no, we're not going to do that. Yeah. Actually, I'm going to restart. I want to pulse width kind of narrow. There we go. All right, so there's one.
They cancel each other.
Right, because they're completely the same wave, and when they hit that fixed barrier, they invert, and they're equal and opposite, and for a moment, there is complete destructive interference, and it looks like there's nothing there. But in fact, there's two waves. It's just that this guy's pulling up at 5, and the other guy's pulling down at 5. And over at this spot, he's pulling up at 3, and this one's pulling down at 3, and this one over here, this one's pulling up at 1, and this guy's pulling down at 1. And so the rope is like, ah! You know, it's being pulled in both directions. Does that make sense? Okay, so here we go. This guy right here, oh man, it sucks to be him. He's like, I don't know which way to go. So he ends up actually just kind of staying there. There it is. This rope is under incredible tension right now. It looks like it's just kind of like staying there. But in reality, there's a wave that's right here, all right? And there's an inverse wave right here that's going this way. And each one of these are being pulled up and down at exactly the same amount, which is why emerge. And they break out there, okay? So it's the same idea, but equal and opposite. I don't know, but you think that's kind of cool. At the very end of this chapter, which I guess will happen sometime early next week, we'll talk about noise canceling headphones, okay? Which analyze the wave that's coming in, okay? And then they send something going this way that's like the opposite. And so it actually, well, they kind of send it in the same direction. That cancels it out. That's if you have the active noise canceling headphones. And so we'll talk about that. The other thing that we'll talk about, and I'm going to see if I can is a standing wave. Amplitude of 0. Go. It's not quite what I wanted. What we're going to try to do, and y'all can help me out with this, what I want to do is I want to send a wave through here, and then as it makes its way back, I want it to completely overlap and then pause it so that it looks just like this. Does that make sense? So that I want it to fit entirely. We need to figure out what. So help me out here, class. We need to find one wave that'll completely fit on here. Like what frequency? That might work. Almost. See that? It's almost. What we're trying to do is trying to get it so that it's just constantly doing the same thing. I used to have written down how to do it, but I don't think I do anymore. Alright, here comes leading edge. It's going back, going back. I think we got a winner here, folks.
Almost. Oh.
We almost have a standing wave. We'll see if we can get one here for you tomorrow before you walk in. But you can see some elements of it when you see one of these guys just standing still. Like, watch this. Like, he's just kind of standing still, and the other parts are just going up and back and forth. Didn't we do this with the?
Yeah,
With the
bro.
ropes.
Yeah, I mean, yeah. It's fun to try to create it in here so that it's just going back and forth. And the idea is there's no friction, and we're just holding it here and holding it here. This thing is just going back and forth constantly. Now, if I change the amplitude, then I'm adding more and more energy. And I think eventually it'll kind of go a little crazy there. All right, let me give you some notes. Just look at this stuff. Lots of fun. Before I walk out the door, just go ahead and I'll have you show me those notes. Just leave those up on your screen. So I'll walk around. You can show me those 10, or 5 or 10 or whatever, how many it was.
I should just like put it in. I'm just like.
I figured. Are y'all pretty much? Are y'all done with this now?
Yeah.
It doesn't want to end. Oh, so that's for this one.
I can't find nice
That's fine.
answers.
All right, here we go.
I don't know.
Is there a blur for anybody? Can all say okay? Alright, so chapter 16. This actually is the last chapter on oscillations, waves, and sound. 14, we talked about oscillations. 15, we started talking about waves. And then this is superposition, standing waves, and I would also say, and sound. Okay? We talked a little bit about sound before. We're going to talk a lot more about sound because sound really comes from standing waves. And before we talk about standing waves, you're talking about superposition, so that's what today's all about. I think it's a didgeridoo. Y'all know what those things are? The Aborigines, they do, it'd be like bow, bow. It's a pretty cool little sounding thing here. All right, so that's what we are gonna talk about. Anybody play instruments? I need to know. Anybody? Yes, yes. A few of you. Okay. I'll let you know. Can y'all bring your instrument to class one of these days? No.
It's a piano.
It's a piano.
Play piano. Okay.
My
What do you bring? What do you play?
trumpet.
Trumpet. Okay.
And ukulele.
Okay. Bring the ukulele too. Absolutely. Ivan, what do you play?
I guess the tuba, piano.
All right. Bring the tuba.
I have a
What is it?
kazoo.
Who does it?
No, if we're not in bed. then we-
Yeah.
Okay. Maybe Kenzie will let us borrow one. Alex, you play anything? No. James?
Trombone.
Please bring a trombone if you can. Anybody else? Piano, you said?
I don't think keyboard thing. I'm like,
Yeah, but keyboard. Yeah, I know. That kind of defeats the purpose of seeing a physical process,
yeah.
right?
No, it's
All right. So, ooh, this is kind of cool. Do y'all see the waves? Oh, looks like they threw some rocks in there. Do you see what happens when one wave hits the other? You're going to have some parts where there's what's called constructive interference, where they like construct a bigger wave, okay? And there's also going to be some points of destructive interference where it's like the wave crest of one wave and the trough of the other collide, and it's like temporarily flat where the water molecules are, like on the rack there. So a lot of the stuff that we're going to be able to visualize, it's easier to visualize with a string, okay, with a standing wave on a string, or with and we'll probably go out there again and have some fun with the slinky and the what do you call it, the other spring. All right, we will talk about how the shape of your mouth affects. Any of y'all vocalists? Do we have any singers out there? Not that you would admit. I'm not going to ask you to sing, but anyway, yeah, everybody sings. at some point. Maybe it's just in the shower or whatever. But or we talk and we'll mention how you change the way you change your shape of your mouth, how that affects the sound. All right, let's go superposition. I don't care about this stuff. What I care about is this. The principle of superposition. Here it is right here. Very big idea in physics. When you've got two or more waves that are simultaneously present at a single point, so in space, the displacement of the medium at that point is the sum of the displacements due to each individual wave. Okay? So you've got one wave coming down the line, another wave coming down the line. There's going to be a point where they overlap, and it's going to create a shape, a displacement of this rope that would be the same as if both of them, were present right there, one on top of each other. And then they're going to continue on their way, never to meet again. Very sad. So this is what I was trying to demonstrate with the simulator there, but we couldn't really make rectangular waves. But imagine if you had a triangle wave coming down the line here, 1 meter per second, and a rectangular wave going that way. No big deal. They're not interfering with each other. Uh-oh, they're about to. And then at the moment when the triangle then first completely covers the rectangle, the shape of the rope will be this like house type thing, okay? Where it would be, the rope would take the shape of the rectangle with the triangle on top of it. And so it would almost look like the triangle is moving along that rectangle. Except for the fact that the rectangle would also be moving this way. Okay, so it'd be like, kind of like that. And at some point, when the triangle was half on, half off, it would be going up here, and then all of a sudden, there'd be a drop, and we would see this part of the triangle. And then they would continue on their merry way, never to meet again, passing completely through one another like two ghosts. Something like that. So anyway, this is constructive interference, okay? It's when both waves are positive and the total displacement of the medium is larger than what it would be for each wave separately. Then you've got the destructive interference, which we saw also. That's when the displacement of the medium at the overlap location is less than it would be if each one of those was looked at separately. So during destructive interference, the energy of the wave is in the form of the kinetic energy of the medium. Okay? Yeah. Okay. Whatever. So there you go. These two guys coming along. We already saw this. There's a moment when it looks like everything is calm, but that's just because they're passing right through each other, right there. And then they go on the rest of their lives. Alright, do you have this problem there on the back page? So as a table, go ahead and answer this one and the next one and the next one. So we've got two wave pulses on a string approach each other at the speed of 1 meter per second. What does the string look like at 3 seconds? So you might need to do some counting. What is it going to look like at 3 seconds?
Because like the rectangle has a bigger area than the triangle, so it's still going to be playing that which you can have like that. It's a hole.
Okay.
That's 2 plus 2.
That's not 2.
But it's moving at what time? It's moving at 1 meter per second.
Okay, well,
That
So
makes
if this
sense.
is here, then this is by itself, so there's nothing like affecting this, so it would be
She's an
like that,
observation.
right? And then
Okay.
this one, this wave is already interfered.
So you need that for sure.
Yeah, and
Gracie,
then
go.
these are equal, so it'd be 0, right?
Mhm.
And then this
How
is
would that
greater,
work though?
this is greater than that. So like,
So what is
'cause
the
it's like half a
triangle being on
triangle,
top?
so the triangle
yeah,
would,
that makes sense.
yeah.
Okay, I see it now. So it is in. It's good to draw it out actually. I understand this more than the history graphs and the
Mhm.
snapshots. Do we do the ones in the back? No, there's none.
Wait, let me see. So it'd be here, at 3 seconds, and then 2, 3.
Alright class, let's go ahead and look at some of these here together. They're both moving at 1 meters per second. So triangle, this is approaching, this is at time t
Yeah.
equals 0. So 3 seconds, this guy's gonna be 1, 2, 3. So it looks like the triangle is gonna be right here between the 3 and the, oh. Magically the answer appears. Triangle is gonna be right there between 3 and 5. The rectangle, 1, 2, 3, also between 3 and 5. So it's going to be the rectangle with that triangle on top of it. Or you can think of it as a triangle with a rectangle on top of it. It ends up with being the same thing, the triangle right here and the rectangle on top. Some of it would drop down and fill this in. So, alright, there you go. Looks good. Answer C. The answer's already there for you, I guess, on this one. So at 3 seconds, 1, 2, 3, they're both between 3 and 5, but this one's below and this one's above, which is why you're looking at answer B there for that one. This is the rectangle with the triangle taking a bite out of it. Destructive interference there. T equals 2 seconds. So at 2 seconds, this rectangle is going to be between the 4 and the 6. The trapezoid is going to be between the 3 and the 6, right?
Mm-hmm.
Okay. I don't know, what'd y'all say?
Okay.
A, because trapezoid between the 3 and the 6, all the way down here. And the rectangle is going to be between the, what was it?
The 4 and the 6.
The 4 and the 6. So, right there.
It helps to draw it out.
Yeah, unfortunately my,
Oh, it won't let you.
It was right.
yeah, I'm not sure why Smarty's not working there. But yeah, see, I think if I, yep, not today.
Pointy.
Okay, so today we talked about constructive interference, destructive interference, how the tension affects the wave speed. We talked about fixed ends and loose ends. What else we talk about? Say it again. Adding waves, yep. Superposition is what that principle is called. That the displacement is what it would look like if those two waves, just add them up, add all the positives, subtract the negatives, and you'll end up where you were. Tomorrow we're looking at 16.2. Let's go over here and look at the agenda for the rest of the week. So standing waves, make sure you have the notes on 16.2. On Wednesday, we've got a quiz. That's a team quiz over chapter 14 and 15. Then on Thursday, more standing waves, but a little bit slightly different stuff there. Having some formulas, that's 16.3. And then on Friday, sound waves. And we've got some good videos for this chapter as well. This is one of my favorite chapters. It's also, I don't know, it's one of the most applicable because it deals a lot with sound, music, instruments, all that stuff. All right, a couple of you, I didn't get your notes. You can kill that.